Today, I'll be introducing the exponential distribution, which is an exciting continuous distribution that's closely related to the Poisson distribution or Poisson process. Recall that a Poisson process is where we have a continuous interval, like distance here, and we have discrete events occurring in that continuous interval. In the example that I talked about before, we have a car and it's traveling along, and we've got potholes. Potholes are discrete events that occur in a continuous interval. If we zoomed in on any subinterval, regardless of how small it is, you can potentially have two occurrences or events that are occurring right next to each other in time. So the Poisson process is when you have discrete events that are just randomly occurring in some interval, a continuous interval. The distribution function for the Poisson distribution is given down here. X here represents discrete events. So this answers the question of what's the probability of getting X number of events in a continuous interval. The mean is lambda times t. T is the period of interest. You can plug that in here and you can estimate the probabilities of a certain number of events occurring in an interval. Using the Poisson distribution, we answered questions like, what is the probability that there will be exactly 6 earthquakes in the next 2 years? And what we did was we calculated a background average rate of occurrence, 200 earthquakes or events per 40 years, and that's 5 per year. If we wanted to answer this question, X would equal 6, exactly 6 events or earthquakes. Our time interval would be 2 years. Lambda t, which is also known as the mean, is equal to, in this case, 5 times 2, and that would be 10. You could plug that into this function with x equals 6, and when you do this, you would get about 6.3%. There's a 6.3% chance that in the next 2 years, there's going to be exactly 6 earthquakes. Now what we're going to do is we're going to ask questions like, what's the probability that there will be at least 3 months until the next earthquake? This is known as the exponential distribution, and x represents a continuous interval. In the Poisson distribution, x represented discrete number of events, but in the exponential distribution, x is going to represent a continuous interval. So we're kind of flipping the Poisson distribution on its head, and we're saying now, instead of what's the probability of getting a number of events in an interval, we're asking what's the probability of an interval between events. In other words, if we were to look at earthquakes, the exponential distribution tells us probabilities related to the lengths in time, in this case, if this is earthquakes, between events. And importantly, it's always the interval between subsequent events. So the exponential distribution describes distance, or length, area, volume, or time between events described by a Poisson process, discrete events occurring on a continuous interval. The random variable x in the exponential distribution is the interval between two events. It is a continuous random variable and can be described by this function. So this is just the little f of x, the non-cumulative. Oftentimes we are interested in the cumulative exponential distribution. So if you integrated this, if you integrated little f of x, you would get capital F of x down here, 1 minus e to the negative lambda x. The mean of the exponential distribution is 1 over lambda, and the variance is 1 over lambda squared. It's a lot easier for you guys to learn if I go through an example. 200 earthquakes in 40 years. What's the probability that there will be at least 3 months until the next earthquake? X then is going to be 3, and it's not exactly 3, it's at least, which means that we're going to be looking for the probability that x is greater than or equal to 3. In other words, if we were to plot x, which is time, and our probability density function for the exponential distribution looks something like this. What we're interested in is 3 months. What's the probability that the next event will occur at least 3 months from now? And so that's represented here by that shaded region. It could occur right at 3.1 months, but it could also occur 10 months or 100 months from now. So we have to sum the area underneath that curve greater than 3. So what we're trying to find is the probability that x is greater than or equal to 3. In terms of cumulative probabilities, how would we write the probability that x is greater than or equal to 3? This is the same as taking 1 minus the cumulative up to 3. F of 3 represents this region here on the left. If we subtract that from 1, because the area underneath a probability density function is always going to be 1, then this will tell us what we're looking for. F of x is equal to 1 minus e to the negative lambda x. Lambda is going to be 200 divided by 40, which is 5 per year. We want to make sure, because x down here is in months, we want to make sure that we convert this to months, so we can multiply 1 year per 12 months, and really lambda is equal to 5 over 12. When we plug this into the cumulative function down here, when I substitute capital F of 3 into here and I subtract from 1, these ones will actually cancel, and what we end up with is the probability that x is greater than or equal to 3 is just e to the negative lambda x. Lambda is 5/12. Our x value is 3. And when we do that, we get the probability that the next earthquake is going to be greater than 3 months from now to be about 0.287. Let me show you how we can do this in Excel. What I'm going to do first is I'm just going to put in a cell here for lambda, and that equals 5 divided by 12, and that's per month. Our x value is equal to 3 months, and we're trying to calculate greater than 3 months. So I can use the expon.dist function in Excel. The x value of interest is 3. Lambda is up here. I've calculated 5 over 12, and I want to do cumulative. So this would give me capital F of 3 up to 3, but in order to get greater than 3, I have to subtract that from 1, and we get the same result that I did using a calculator. Let's go through one more quick example. Same scenario. What's the probability that the next earthquake will occur between 2 and 5 months from now? Again, we have x in months. We have little f of x here. The exponential distribution looks something like this. And we're being asked, what's the probability that starting now, the next earthquake is going to occur between 2 and 5 months, which represents this shaded region? How would we determine that probability in terms of the cumulative function capital F of x? We could take capital F of 5 and subtract capital F of 2, and that will give us the probability that we are looking for. And so I can type this in here, the exponential distribution of 5 months with our lambda up here. I want to be cumulative, capital F. I do the same thing, but x equals 2. And when we do that, and we get about a 31% chance that the next earthquake will occur between 2 and 5 months from now. Thanks for watching this screencast on the exponential distribution.